Na festa do fim de semana, só um rolê bom. Ela chega e desencana com passo bem sou, passo bem sou, passo bem sou. Na festa do fim de semana. Festa do fim de semana, só um rolê bom. Ela chega e desencana com passo bem sou, passo bem sou. Na festa do fim de semana, semana, pana, 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 pana. Na festa do fim de semana. Pana, 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 de semana. Pana, 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 de semana. Pana, 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 de semana.
Hello everyone and welcome to my new stream. Today we are gonna do something different. Yeah, I wanted to learn more about OpenGL, but there is a problem. The fact is, like, this is my time, okay? This circle is a graph, is a cake graph about my time, and this is like this is hold on, let me just pick two colors. So we have two colors here, right? This is how much I spend time for my uni and studying it and things like that, and this is how much I do things for my projects, right? So this is my time, right? And this is how this is how much I spent for my project. This is how much I spend for work. Yeah, there is no space here, and that's a problem because I'm studying for software engineering, so we should have more time for this, right? And I've decided to to start studying it. Yeah, this is pretty much how we that's pretty much what we are gonna do, right? Yeah, we have this part here, like we should, like, this should be we should increase this part right here. So yeah, this is pretty much how I spend my time. So not a good thing. So yeah, and to do that, I decided to learn to to start from this book that I found online, and this book is about mathematics for machine learning. So a very useful topic. And on software engineering, of course, you study you cover things like linear algebra, and that can be really useful when we render engines. So if we so linear algebra, like, is very useful if you want to uh, you you want to create AI models or lar- large language models, right? And then we have 3D 3D engines. So this could be really useful for this stuff, right? And there are other things that where computer science is involved. So it's really important. That's why I decided to to study this from scratch. Lately, I'm doing this all of this on live stream. I know some basics, but I know very little about these topics. So, and I decided to stream it because I noticed that when I stream, I somehow focus better on things. It helps me focus, and it helps me document and keep track of what I'm doing, um, and so on. And this could be useful for viewers that to 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 learn more things, I guess, or um, to refresh memory or things like that. I don't know, but one thing before we start, I want to thank you so much for 8 subscribers. Like, wow! Uh, Thank you so much. I saw your comment. Here it is. He's trying to learn OpenGL, like me, like I'm doing, and I'm so happy that you find your my stream helpful, and you use like my examples to learn more things that can be useful for your projects. And then like I wanna thank you a lot for this. I didn't expect people to come to my channel, um, and we are basically building a little. It's for now. It's a small community where some I got a few DMs on Discord or any other platform where people uh, asked me questions about issues they had on JavaScript, and they asked my help, and I'm really happy to I'm really happy to to try to help. I'm glad you you somehow trust me. uh, it's a beautiful thing, actually, and I wanna continue streaming. I only got positive results. I can focus more. I can document stuff, improve my English skills, and do like keep track of what I'm doing and meet some people. Like it's a win-to-win situation, right? It's a win-to-win thing. So that's cool. That's cool. For now, I didn't. I I haven't uh, like I haven't found any negative any cons about live streaming or stuff on YouTube. I'm glad for this. Now let's start. Let's start learning this. So this is an open source book. The name is MML book. You can search it here. It's mathematics for machine learning, and it's published by Cambridge University. And you have like this isn't I'm not going like for I'm not currently on Cambridge University, so I'm I'm not there, but I'm using this book and it's open source. Here it is. Like you have you have some resources here, and that's what we are gonna read today. Like we are gonna start reading this and look at this. There are so many pages. I doubt we can read everything in one single stream, but but let's get started. So this is the book again. Yeah, let's try to read this book and try to understand something about this, because I'm not really good. So holy shit. Let's get started. So we have uh, we have this part here. We have a little introduction. I would read this book entirely just to understand things properly. Yeah, maybe we can skip this part. I mean, that's okay. Oh, we have the table of symbols. Let's see. Okay, scalar values are, if I remember correctly, scalar values are atomical values. Oh my god. It's like a number. It's a number, right? Like we don't it's we don't have it defined this, like if it's inside this the real numbers, or this like could be any of that, right? And vectors are bold lowercase, and the vector is like a set of values, like in a row. This, I mean, a vector is something like this, right? Then we have matrices. It's are bold uppercase. Then we have, this is transpose of a vector or a matrix. That's the inverse of a matrix. This is the inner product of x and y, and honestly, I don't know what a inner product is, but we will find that. But I will find out. I will find out soon. This is the dot product of x and y. This is a ordered tuple. Okay. This is a matrix of column vectors stacked horizontally, and this is a set of vectors. Okay. So this is a set of vectors. Okay, this is a set. This is a matrix of vectors, right? And this is a tuple. Okay. Okay. I don't know what this is a tuple. Like tuple are uppercase and italic. No, are just uppercase. Okay. This is integers and natural numbers. Okay. We have integers and natural numbers, right? Then we have real and complex numbers. Okay, and then we have the vector space, right? We should have a metric space that, like, for real numbers, a metric space should be like something like this, if I remember correctly, right? So let's keep going. This is a universal quantifier for all. Okay, this is quite confusing because this is in English. Like I'm studying this. I usually study maths in Italian, and this could be a little bit tricky. And it's in Italian is per ogni x. This is esiste, quindi existe un quantifier, there exists x. So for all x, there exists x. So we should remember this. Okay, this is the definition, and this is the definition, but the operands are reversed, right? And this is proportional, if I remember correctly. Yes. What are this? Function composition G after F. I have no idea what it is. So yeah, we have if and only if, then we have implies, then we have sets. This is a set, right? So the set is something like this. And yeah, and then we have A is an element of set A. So in Italian is appartiene a, cioè l'elemento A appartiene all'insieme A. Cioè, so it's quite confusing when you like learn a math in another language. So A is so we don't specify this as an element. So A is we specified right here is an element of set A. Okay, this is quite the syntax, like the human language syntax is a little bit different. Like A is an element of set A. Okay, then we have an empty set, and it's usually not a zero. It's just the void symbol. They're quite similar. Probably they're the same. It's the exact same symbol. Yeah, they're exact same symbol. For some reason, this is more oval. I don't know. It looks like a zero, but yeah, it's this part here. Okay. There we have, this is the subtractions, right, of sets. A without B, the set of elements but not in A but not in B. Number of dimensions indexed by D. Uh, I have no idea what that means. Then we have identity matrix size of m times m. Then we have matrix of zeros, m times n, matrix of ones. Okay. Let's the identity matrix, it should be something like this, if I remember correctly. Let's try to check. Like, it should be something like this, right? So we have this. This should be identity, right? This is this is like something. Let's move this here. It's something like this. So we have this of this should be this, right? Not sure. I'm trying to remember things. Let's see. Yeah, I'm right. Yeah, this is okay. Yeah, we get it. So it should be, actually, the right notation is not like that. What am I doing? The right notation is I3. This is the right notation, right? So this is a matrix 3 times 3 of this is an identity matrix, right? Then we have E, standard canonical vector, where I is the component that is 1. What does that mean? Honestly, I have no idea what that means. Then we have dim, dimensionality of vector space. Then we have the rank of a matrix, the image of a linear mapping, and what is this symbol? That's phi, right? Yeah, it's phi. And that's the kernel. Then we have the span, the trace, the determinant. Then we have the absolute value of, or determinant depending on the context, the norm. And then we have eigenvalue or Lagrange multiplier. Eigenspace correspond to eigenvalue. Okay, I understand like 60% of the things so far, but this is just the table of symbols, right? And oh, we have more. Okay, this is the orthogonal. Okay, this is where when vectors and x and vector y are orthogonal. No idea. Then we have vector space. Okay. Then we have orthogonal component of vector space. Then we have the sum of x and x1 plus, yeah, this until x and, oh, okay, I know what that means. Okay, in my university, like they wrote this, they always write this lowercase. Yeah. Then we have the product of the x of n. I'm not sure if I'm pronouncing this correctly. Then we have parameter vector. Then partial derivative of f with respect to x. Total derivative of f with respect to x. Then we have the gradient. I have no idea. Now we have the smallest function value of f. Okay. Uh, okay, the smallest function value of f. Then we have the value um, that minimizes f. Okay, there are so many. There are some symbols that I never seen before, like this two, and um, then we have some wordings, some acronyms. Exempli Gracia, Latin for example, Gaussian, Gauss, oh my god, Gaussian mixture model, IDS. This means independent, identically distributed, maximum a posteriori, maximum likelihood. Oh, okay. So now we have the introduction, right? Uh, for if we encounter some symbols that we don't know, we always have this table, right? So we can always come back. It's just a book, luckily. So this is pretty much we how we're gonna handle this problem, right? Okay, so let's get started from the introduction and motivation. Yeah, because we need that. Oh my fucking god. Okay. I forgot how to drink water. Okay, let's get it started. Um, so, machine learning is about designing algorithms that automatically extract valuable information from data. The emphasis here is on automatic. Wait, hold on. IDS. This means okay. Uh, the emphasis here is on automatic. This means machine learning is a concerned about general-purpose methodologies that can be applied to many datasets, while producing something that is meaningful. There are three concepts that are at the core of machine learning: data, model, and learning. Okay, that's cool. That's cool. So we have machine learning is about designing algorithms that automatically extract valuable information from data. So So we have like it's like we have is a box, right? This is and this is full of data, right? What we do is we simply put this. Oh my god, I'm so fucking bad at drawing arrows. What we do is we process this, right? We process this information. I'm not good at drawing things, but and this is the um, what that is. This is machine learning, right? Um, yeah, I call it and this is like basically what it does is it extracts from this box. It extracts like important data, like this this these are important data, or values, right? The values we need from this box, right? This is what it does. Like these are like stored inside of this box um, with other data, with other values, right? For what I understand, and then we process this and we extract this part right here, and like this is a set like of algorithms, right? Designing algorithms. So it's like algo, right? And we have and there are three concepts at the core of machine learning: data, a model, and learning. Okay. Uh, since machine learning is inherently data driven, data is at the core of machine learning. The goal of machine learning is to design general purpose methodologies to extract valuable patterns from data. Yeah, that's what we. Okay, okay. So we have we don't simply have to extract valuable data, but we should also extract the patterns from data, right? Um, okay. Ideally, without much domain-specific expertise. For example, given a large corpus of documents, for example, books in many libraries, machine learning methods can be used to automatically find relevant topics that are shared across documents. Oh my fucking god, where the fuck did I ended up? Wait. Oh my god. Oh, hold on. Let me check. Okay. To achieve this goal, we design models that are typically related to the process that generates data similar to that dataset we are given. For example, in a regression setting, the model will describe a function that maps inputs to real-valued outputs. To paraphrase Mitchell, Wait, hold on. Mm, Okay. To paraphrase Mitchell, a model is said to learn from data if its performance on a given task improves after the data is taken into account. The goal is to find good models that generalize well to yet unseen data, which we may care about in the future. Learning can be understood as a way to automatically find patterns and structure in data by optimizing the parameters of the model. So, okay, so we have data, right? We have data that is at the core of machine learning and is to extract valuable patterns from data. Okay, for example, okay. Um, okay, to achieve this goal, we design models that are typically related to the process of that generates data. So models generates data, right? Okay, similar to dataset we are given. Okay, while we have learning that can be understood as a way to automatically find patterns and structure in data by optimizing parameters of the model. So basically what that means is we have, okay, this is like this is a machine learning, right? Okay, let me just hold on, let me just move everything here to save space. So we have this part here, and then we have this part here. Okay. Uh, Actually, I will just delete that. Or nah, but I will definitely shrink this part because it's taking so much space, right? So what we have, this is our machine learning thing. I don't know how to call it right now. There we have this is and this contains our data, like it's like we have a data, right? Then we have a model, right? Wait, we have a model that generates data. Probably, I don't know how to draw this, but we have this a model, and then we have the learning, learning. This is the concept, right? Then we have learning. And for what I understand so far is that we give data, right? And the learning part find the patterns, right? So we have the patterns get, and then we have the model that generates other data, right? Oh god. For what I understand, I'm not sure, but it is what I understand from here. Because the we like this book specified that we have to design a model that are typically related to the process that generates data. So this generates data, and the data should be similar to the data set that we are given. But to do that, we must learn the patterns, and this is what the learning process does, right? So this is like how pretty much how it works. Also, let me just make this arrows on different colors so we can understand it better. So we have, hold on. So this is pretty much how it works. Like we have some data, we learn from it, like we find some patterns, and then we generate other data. While machine learning has been many success stories, and software is readily available to design and train rich and flexible machine learning systems, we believe that the mathematical foundation for machine learning are important in order to understand fundamental principles upon which more complicated machine learning systems are built. Okay. Understanding these principles can facilitate creating new machine learning solutions, understanding and debugging existing approaches, and learning about the inherent assumptions and limitations of the methodologies we are working with. That's cool. That's cool. So, okay. So this is for what I understand that machine learning is have this free process, right? Okay. That's cool. That's cool. Let's keep going. So, uh, 1.1 Finding words for intuitions. So, a challenge we face regularly in machine learning is that concepts and words are slippery, and a particular component of the machine learning system can be abstracted to different mathematical concepts. For example, the word algorithm is used in at least two different senses in the context of machine learning. In the first sense, we use the phrase machine learning algorithm to mean a system that makes predictions based on input data. So, the generated data should be like the predictions should be part of the generated data, right? So we can use this as an example. Like we have hold on, we have predictions, right? Yeah, this is basically how it works, right? And this is the generated data. Probably should be like that. So yeah, the generated, so yeah, it makes sense because like there are some algorithms that read some data and then it generates, do you know like crypto mining broker things like that? They have some algorithms that predicts uh, the the markets, like the stock values, things like that. There are like graphs that are generated by these machines, right? It is something like this. So it's used. The word algorithm is used in two different senses. So the first is machine learning algorithm. It's to predict things, right? That's called a predictor. And then we have in the second sense, we use the exact same phrase machine learning algorithm. Okay, that's a little bit confusing, but okay. To mean a system that adapts some internal parameters of the predictor so that it performs well on future unseen input data. Wait. Okay. Here we refer this to adaptation as training a system. Okay. This book will not resolve the issue of ambiguity, but we want to highlight upfront that, depending on the context, the same expression can mean different things. Oh fuck! I'm I'm not that happy to hear that information, and this can be quite confusing. However, we attempt to make the context sufficiently clear to reduce the level of ambiguity. Oh, at least they are trying, right? The first part of this book introduces the mathematical concepts and the foundation needed to talk about three main concepts of the machine learning system: data, models, and learning, right? And the things we wrote here. We will briefly outline these components here, and we will revisit them again in Chapter 8 once we have discussed the necessary mathematical concepts. While not all data is numerical, it is often useful to consider data in a number format. Okay, so data should be a number format, always, right? We should always consider them as a numerical value, right? In this book, we assume that data has already been appropriately converted into a numerical representation suitable for reading into a computer program. Therefore, we think of data as vectors. Okay, that makes sense. As another illustration of how subtle words are, there are at least three different ways to think about a vectors. A vector as an array of numbers, a computer science view, a vector as an arrow with a direction and magnitude, physics view, and a vector as an object that obeys addition and scaling, mathematical view. Okay, so this should be treated as numbers, right? This should be, I don't know, we should tokenize this as numbers. Like if we go here, data should be treated them as numbers. So if we have like some words, we should convert this into a numerical format. I'll just call it n, right? Because this is pretty much how maths work. Like it does operations on. It usually operates on numbers, right? That are, and in this case we have to to convert the words or any formats into numbers, right? And on this book they will treat they will treat data as vectors. So I think they mean like data as a set of numbers, right? A set of values, something like this. Probably, but data are vectors, okay? Data, like, it kind of makes sense because this is like a set of data of values of elements. I don't know how to call this, so I will just put this here, right? So we can consider data as a vector. So this is a D. Oh, sorry, this is a matrix. So I will probably indicate vectors like this, right? And this is a vector of data, right? Of values or anything like that. And hold on. A model is typically used to describe a process for generating data. So yeah, as we mentioned before, this is generating data similar to the dataset at hand. Therefore, good models can also be thought of as simplified versions of the real unknown data processing process, capturing aspects that are relevant for modeling the data and extracting hidden patterns from it. A good model can then be used to predict what will happen in the real world without performing real-world experiments. Yeah, that's cool. This is basically why maths exists, like mainly. I mean, mainly, not mm, like we can experiment things mm, without doing it on reality, right? Then we have learning. We now come to the crux of the matter, the learning component of the machine learning. Assume that we are given a dataset and a suitable model. Training the model means to use the data available to optimize some parameters of the model with respect to a utility function that evaluates how we model the how well the model predicts the training data. Most training methods can be thought as an approach of analogous to climbing a hill to reach its peak. In this analogy, the peak of the hill corresponds to a maximum of some desired performance measure. However, in practice, we are interested in the model to perform well on unseen data. Uh, Probably. Desire the performance measure. However, in practice, we are interested in the model to perform well on unseen data. Performing well on data that we have already seen, training data, may only mean that we found a good way to memorize the data. I can't think about an algorithm. Uh, what's the fucking name of that process? I don't think it's nothing related to machine learning, or maybe it is related, but this made me think of mm, polynomial um, Wait, is it the... Yeah, something like this, but it was a little bit different. Wait, this one, polynomial interpolation. Yeah, it reminds me of something like this. Like, we have some data, right? And the and the and the process of polynomial interpolation is, if I remember correctly, is to attempt to create a graph or a function, right? Using some points on the graph, right? Using some values. That's what it reminds me of. I wanna write these algorithms in assembly language. I think that would be very interesting, right? We should do that one someday. Not right now because I'm incompetent as fuck, but when we learn all of this, we can proceed, right? Okay. There are two ways to read this book, okay? However, in practice, we are interested in the models to perform it. Okay, we already read this. However, this may not generalize when to unseen data, and in practical applications, we often need to expose our machine learning system to situations that it has not encountered before. That can be a problem, yeah. Let us summarize the main concept of machine learning that we cover in this book. Okay, this is the key points of this topic, right? We represent data as vectors. Okay, so we should always remember that data are vectors. Okay, data are vectors. So this is like this is data, right? They are vectors. Okay, so yeah, it should be. Then we choose an appropriate model, either using the probabilistic or optimization view. So we have to choose the right model, okay? We learn from available data by using numerical optimization methods with the aim that the model performs well on data not used for training. Okay. Okay, this is okay. I already read this part. Like, there are two ways to read this book, and the thing is, the first half of this book, it covers the mathematical, theoretical part of this topic, and then the second part, it focuses on algorithm, like programming part, the practical parts, things like that. But right now we are studying for university, and we want to learn linear algebra properly. So we are focused on the first part, but I'm also interested on the second part. But first we have to learn linear algebra and things related to that, right? Okay. So we have okay, this is machine learning, and we have regression, we have dimensionality reduction, density estimation, and classification. We have okay, that's interesting. We don't just have linear algebra, we also have all of this stuff. That's interesting. That's what we need. We need to learn all of this, okay? Very nice. So right now we have all of this stuff right here. This is what we. This is like the introduction of the um, of the book. Yeah, and then we can finally start the linear algebra. And before doing that, I don't know, but learning new things that are like learning things that are completely, almost completely new to me is kind of tiring. So I'm gonna make some little break, and then we are gonna proceed. So right now I will be right back in a few minutes. So see you later. Okay, time to come back, I guess. So I didn't rest properly, but I just wanna start learning algebra. So let's go. Let's get it started. So when formalizing intuitive concepts, a common approach is to construct a set of objects, symbols, okay, and a set of rules to manipulate these objects, right? Hold on, let me just, okay. This is known as algebra. Wait, huh? And a set of rules to manipulate this object. Okay. Linear algebra is the study of vectors and certain rules to manipulate vectors. Okay. The vectors many of us know from school are called geometric vectors, which are usually denoted by a small arrow above the letter. Okay, this is pretty much what I did here. Like, this is a vector, right? In this book, we discuss more general concept of vectors and use a bold letter to represent them. This is like, well, for like we've seen it before, we use the bold letters. In general, vectors are special objects that can be added together and multiplied by scalars to produce another object of the same kind. From an abstract mathematical viewpoint, any object that satisfies these two properties can be considered a vector. Here are some examples of such vector as objects. So we have geometric vectors. This example of a vector may be familiar from high school mathematics and physics. Geometric vectors are direct segments which can be drawn in these two dimensions. Geometric vectors x and y can be added such that x plus y equals to z is another geometric vector. Furthermore, multiplication by a scalar. Oh, wait, what the fuck is this? Furthermore, multiplication by a scalar. Lambda is a scalar value. Okay, where lambda is set of R. Is it a set of? Wait, hold on. Set. Is it set of, right? Where is it? Oh my fucking god, where the fuck is this shit? Okay, I mean, is an element of set. Okay, this is how it reads. Is an element of set. Okay, an element of set. Okay, I got it. So, lambda is an element of set R of real numbers. Like that, right? So, lambda multiplied by x, and lambda is an element of set of real numbers, of the set of real numbers, right? It's also a geometrical vector. In fact, it is the original vector scaled by lambda. Therefore, geometrical vectors are instances of the vector concept introduced previously. Interpreting vectors as geometric vectors enables us to use our intuitions about direction and magnitude to reason about mathematical operations. Polynomials are also vectors. The fuck is this? Two polynomials can be added together, which result in another polynomial. Oh, okay, that makes sense. So we can add like these lines together, right? To create another polynomial. Like we we add two functions, two polynomials, and we get another polynomial, right? Yeah, exactly. Be added together, which should result in another polynomial, and they can be multiplied by a scalar. Lambda is an element of set of the real numbers, right? And the result is a polynomial as well. Yeah, that's true. That's true. Therefore, polynomials are rather unusual instances of vectors. Note that polynomials are very different from geometric vectors. While geometric vectors are concrete drawings. Okay, yeah. Polynomials are abstract concepts. However, they are both vectors in the sense previously described. So they are like polynomials and yeah. And polynomials are just more as a more abstracted concept, right? Audio signals are vectors. Audio signals are represented as a series of numbers. We can add audio signals together and their sum is a new audio signal. That's true. But isn't an audio signal a polynomial? Like it's a function. Like isn't like I don't know. We can okay. So audio signals are vectors, okay? If we scale an audio signal, we also obtain an audio signal. That's true. Therefore, audio signals are a type of vector too. Yeah, that's true. That's true. So audio signals are also vectors. Like vectors are everywhere, right? Elements of tuples of n real numbers. I have to memorize these terms because this is in English is a little bit different and it might be confusing. Elements of tuples of real numbers. So this is a tuple of n real numbers. Okay, are vectors. Yeah, that's true. That's true. Tuples can be considered as vectors, right? Tuples of real numbers is tuples of n real numbers. Okay. I have to memorize this. So tuples of n real numbers is more abstract than polynomials, and it is the concept of and it is the concept we focus on this book, for instance. So we have A, and A is a vector, right? It's lowercase and bold. Then we have it's a vertical, like it's a column vector, right? And this is an element of this set of an element of tuples of three real numbers. Okay, so this vector is an element of the set of a tuples of three real numbers, for what I can understand, right? Probably it is like this. Like it's probably like this. It is an example of a triplet of numbers. Adding two vectors a and b and as element of tuples of n real numbers component y results in another vector, a plus b equals to c, and it's also a set of a tuple of a real of three real number of n real numbers. Sorry, this is quite confusing because there are English terms, and moreover, multiplying a set of the tuples of n real numbers by lambda. This is a set. This by lambda as an element of this set of real numbers results in a scaled vector. So hold on, because I had to translate this in English and I couldn't focus on the text. Moreover, multiplying a by lambda, so multiplying a vector by a scalar value results in a scaled vector. Lambda times a is a set is an element of set of the tuple of n real numbers, right? How will we get used to this? Considering vectors as elements of tuples of n real numbers has an additional benefit that it loosely corresponds to arrays of real numbers. Okay, yes, yeah, it's basically the same thing, right? On a computer. Ooh, that's interesting. Many programming languages support array operations, which allow for convenient implementation of algorithms that involve vector operations. And guess what? C is not one of them. Like, C doesn't support vector multiplication and things like that. Like, you have to implement it by yourself. It's kind of interesting. I want to create some algorithms to handle these operations and create like an architecture with a set of these mini softwares written in a low level language that can perform operations, and we can pull out some interesting things, right? The only thing we need is to read fucking books and learn everything we have to know, right? Linear algebra focuses on the similarities between these vector concepts. We can add them together and multiply them by scalars. We will largely focus on vectors in tuple of n real numbers. Let me reread this again. We will largely focus on vectors in tuples of n real numbers. Again, we will largely focus on vectors in tuples of n real numbers, right? Yeah. Since most algorithms in linear algebra are formulated in tuples of n real numbers. We will see in Chapter 8 that we often consider data to be represented as vectors in set of n real numbers. In tuples of set of. Oh my God! We often consider data to be represented as vectors in tuples of n real numbers. In this book, we will focus on finito-dimensionali. We'll focus on finite-dimensional vector spaces, in which case there is a one-of-one correspondence between any of vector and tuples of real numbers. Okay. When it is convenient, we will use intuitions about geometric vectors and consider array-based algorithms. Okay. Okay, that's kind of interesting. So this is a tuple, right? This is a tuple of n real numbers, right? Can we just scroll up and where is it? Let's memorize. Wait. Where the fuck is the fucking table? I forgot. Here it is. Let's memorize this page 12. So this is okay. This is an n-dimensional vector space of real numbers, and this is literally the definition of tuple, right? Probably, but they call this a tuple of n real numbers, and it's n-dimensional vector space of real numbers. It's kind of the same thing, right? Yeah. So yeah, linear algebra. Let me reread this again. Linear algebra focuses on the similarities between this vector concepts. We can add them together and multiply them by scalars. Okay. We will largely focus on vectors in tuple of n real numbers, since most algorithms in linear algebra are formulated in tuples of real numbers, or or vectors of real numbers, something like this, and n-dimensional vectors of real numbers. We will see in chapter 8 that we often consider representatives of vectors in R, and I will call this Rn, I don't care anymore. In this book, we will focus on finite-dimensional vector spaces, in which case there is a one-of-one correspondence between of any kind of vector and n-dimensional vector space of real numbers. And it is convenient, we will use intuitions about geometric vectors and consider array-based algorithms. One major idea in mathematics is the idea of closure. Closure. This is the question. What is the set of all things that can result from my proposed operations? What is the set of all things that can result from my proposed operations? Okay. In the case of vectors, what is the set of vectors that can result by starting with a small set of vectors and adding them to each other and scaling them? This results in a vector space. The concept of a vector space and its properties underlie much of machine learning. The concepts introduced in this chapter are summarized in figure 2.2. So we have the systems of linear equations, and what the fuck is this, honestly? So we have the vector, and the vector is a property of linear independence. Okay. And then the vector composes a matrix, okay, which represents a linear affine mapping or a system of linear equations. Okay, this is more familiar. Yeah, we can. I know really well that we can use metrics to solve linear equations, right? Solved by Gaussian elimination. Yep. Then we solve matrix inverse. Then we have like a group uh, that can be represented by vector space. Yeah, this is pretty much the, like this is a map of the concepts that are related to vectors, right? Resources are Gilbert Strings Linear Algebra course and myths and the Linear Algebra series by Free Blue One Brown. Okay, that's interesting because I know Free Blue One Brown. Linear algebra plays an important role in machine learning and general mathematics. The concepts introduced in this chapter are further expanded to include the idea of geometry in chapter 3. Okay, that's good because like they are summing up what we are going to do. In chapter 5, we will discuss a vector calculus where a principled knowledge of matrix operations is essential. In chapter 10, we will use projection to be introduced in section 3.8. For dimensionality, for, for, dimen, for dimensionality reduction with principal component analysis (PCA). In chapter 9, we will discuss linear regression, where linear algebra plays a central role for solving least squares problems. That's interesting. Okay. This is can I remove this thing here? No, I can't. Can you please do it? Please fucking remove it. Yeah. Okay. I guess I just sit there. So we finally we are finally reached the systems of linear equations. Okay. So system of linear equations plays central part of linear algebra. Yep. Many problems can be formulated as system of linear equations. Okay. And linear algebra gives us the tools for solving them. Okay, that's cool. Okay, so we have a problem that can be translated to a system of linear equations. To solve these problems, to solve these linear equations, we use linear algebra. And then, yeah, basically like this. A company produces products N1 to Nn for which resources R1 to Rm are required. Okay. To produce a unit of product Nj um, a ij units of resource I are needed, where I equals to 1 to m and j is 1 to n. The objective is to find an optimal production plan, for example, a plan of how many units xj of product nj should be produced if a total of bi units of resource ri are available. Ideally, no resources are left over. Okay, let me just reread this. So what do we have here? Like, hmm. So can I just wait? Can I just close this part? I need to close some. I have to eject this part, this drive, but for some reason it doesn't allow me to eject it. Why are you doing this? Which program is using this? So let me hold on. Let me just. Okay, so let's see if I'm still streaming or not. Yeah, I am. Let me just check my YouTube channel. Okay. So we have okay. So we have a company that produces products, and this is this a matrix? Products N1 to Nm, for which resources R1 to Rm are required. To produce a unit of product, Nj, Aij units of resource Ri are needed. That makes sense. Like A is the quantity, right? A of Yj, I mean A of Ij units of resource I are needed. Okay, that makes sense. And okay, I is 1 to m, right? Yeah, because we used I for the resources, right? And the products we use the j value, right? Yeah, of product nj. So this represents the quantity of units of the resource are needed.
Okay, and I and J is 1 to N, yeah, because we use it right here, right? The objective is to find an optimal production plan, a plan of how many units X of products of units Xj of product and J should be produced if a total of Bi units of resource Ri are available and ideally no resources are left over. Okay, let me try to understand this. So we have abbiamo l'obiettivo, questo, quindi un piano per... Okay, so this is how many units we produce. Xj of product Nj. Wait, how many units? So this is the quantity of the units, right? Yeah, how many units of product should be produced if a total of Bi units of resource Ri are available and ideally no resources are left over. So we have N products and R resources, right? Like N is an array of products because we have different products and we have different resources. And then we need Aij units of resources of resource Ri are needed. If we produce x1 to xn units of corresponding products, we need a total of AI1 x1 plus AIN times xn. Many results of resource Ri an optimal production plan x1 to xn as an element of Rn. Therefore, has to satisfy the following system of equation. Okay. So hold on. So x of j, I don't know. Okay. Okay, I get it. I get it. Xj of product nj. Okay, this is the quantity of nj should be produced if a total of bei units of resource are I are available, and ideally the resources are left over. Okay, I get it. I get it. Okay. The things that confuses me that they used j to represent n and I to represent like the index of R, and like that confuses me a little, but I got the point. So B is the amount of reserve of each resource we have, right? B is a tuple, right? Then we have another tuple that is like how many units. So this is the value that we have to find, right? Uh, how many units of row, and b is like the input value, and then we have okay. So what a is. Okay, A is a matrix, right? A is a matrix that tells us how many units of the resource Ri are needed to to produce uh, xj. But we have a bi units of the resources, right? So aij like cover everything actually. So with this with this mm, operation, we will find wait, I'm not gonna read this. I'm trying to understand by myself. AY1 to N IN times XN. So X is the how many units, right? How many units? Then we have Y. So this is how many resources we need, right? This is tells us how many resources we need, right? So we would find the BI, probably BI. Let's see. So this is many units of resource Ri, which is BI, right? Exactly. Wow. Exactly. That's what we did. Exactly. We found BI. We found the vector. So this is interesting, right? Okay, okay. I was right, right? We can see it, right? And then, okay, okay. So I took some time to understand, but I actually managed to understand also. Let me just. I'm laying on bed right now. I moved from the desk. Let me just. Uh, let's see if I can draw on paint using my. No, I cannot. Hold on. Let me just grab my mouse. Okay, so I have my mouse right here. It's connected to my PC. Let me just okay. Hold on. Oh my god. So we have so for what we know, we have N J, right? Wait, hold on. What am I doing? N products, right? Then we have R I resources. I mean M. So we use J and I to indicate the resources, right? Then we have an A of resources that we need to produce n, right? So for each n, so like this contains the amount of information. Wait, that's not completely correct. So we have right here, we have x of j, right? Of product nj. Yeah, because this is pretty much the quantity we need. Then we have, then we should, if a total of pi units of resources are available. So we have how many resources we need, and this is like this is the quantity, right? Let's mark. Okay, all of these vectors, like the lowercase vectors, are like represents the quantity, and this represents the like the product or the product itself, right? So we have b we have b quantities for each resource, then we have xj for each quantity, right? Let me just do this like this. And then what we need is we need the amount of resources to produce xj, the quantity of xj of n, right? I mean I mean nj, sorry. So what do we need? We have to find how many resources we need, right? So for each bi, we would probably need the quantity of xj, right, multiplied by how much we want, like, and this makes sense. This actually makes sense. Like, let's give a concrete examples, right? So we have like let's give concrete examples. We have n, which is, you have I don't know, you have triangles, squares, and circles, right? I don't know, I cannot make any better examples. Then we have the resources, right? We have points, then we have sides, and then we have, I don't know, fill or anything like that. We can have another element, probably plane, like things like that. So for the triangle to produce this amount of triangles, right? We need this amount of resources, and we should simply multiply this. So it's it's really easy. It's so basic. The only thing is to understand, to interpret this text, right? That was the only issue that I had. That's why I stood here for minutes, because I could understand what this text actually mean. Now we know, and it's actually really easy. So equation 2.3 is general form of a system of linear equations, right? Yes, this is the general form. Wait, yeah, this is the general form because it's like b1 to bm, like we didn't specify anything, and x1 and xn are the unknowns of this system. Wait, they are known? What? Oh, okay. So it's the opposite way. So uh, this isn't the unknown. Okay, that I got confused. But the point still is the same. The actual unknown is this. This is the unknown, and we create linear expressions like this to to find each value of x, right? So this is pretty much how it works. We have a system of linear equations, and I honestly I don't know what it's doing right now. Like, what is this? Like, where does this come from? Like, we have this, but where does this come from? Is this related to the previous example? Or it's completely unrelated? This is probably unrelated because that wouldn't make any sense. So we have the system of linear equations x1 plus x2 plus x3 equals 3, and we have x1 minus x2 plus 2x3 equals 2, 2x1 plus 3x3 equals to 1. Has no solution. Adding the first to adding the first two equations yields 2x1 plus 3x3 equals to 5, which contradicts the third equations. Okay, even if we have this part, like 2x1 plus 3x3 So this would be okay. So this would be equal to 5, but no. Yeah. I can try to substitute this. And just try to understand this properly. So we have x1 minus x2 is 2x3. So 2x1 plus 3x3 is not 5. Yeah, that makes sense. Yeah. Yeah, there is no solution, yeah, because this invalidates everything. Let us have a look at the system of linear equations. Okay, equals to 3 x1 minus x2 plus 2. Okay, this should be valid. This should be valid, right? This should have a solution. Everything should be 1, right? Probably. From the first and third equation, it follows that x1 equals to 1. From 1 plus 2, we get 2x1 plus 3x3 equals to 5. x3 equals to 1. From 3, we can get that x2 is equals to 1. Therefore, 1 is the only possible and unique solution. Verify that 1 is like the 2 poles of 1 is a solution by plugging in. As a third example, we consider this. x1 plus x2 plus x3 is 3. We have x1 minus x2 plus 2x3 is equals to 2. Okay, so this is probably 1. Once again, probably, or wait, it's different because if we sum, oh wait, it's actually the same thing. So this is actually, it actually, yeah. So this is the, so if we put here 5, everything is valid, right? And we get 2x1 equals 5 minus 3x3 and 2x2 equals to 1 plus x3. We define x3 equals to 1 as an element of set R has a free variable such that any triplet. Oh, that's cool. So we have many solutions, if I get it correctly, right? Yeah. Okay. Let me take a short break, and I will be back soon. Okay, we are back. So let's keep going. Then we have the systems of linear equations, right? Let's see. Wait. Hold on. This is the continuation of this part here. This is kind of confusing actually. So we have the free variable, and it is divided by 2 because it was multiplied by 2 before, right? Uh, Wait. Probably. So we set a x3 as a free variable, right? But I don't understand why the other values are divided by 2. Oh wait, I should look at this equation. So we have this, right? And this is actually all right. Okay, I get it. Yeah, I get it. Yeah. In general, for a real evaluated system of linear equations, we obtain either no exactly one or infinitely many solutions. Linear regression solves a version of example 2.0. This, wait, can I, yeah, this is the of that problem but we cannot solve the system of linear equations. Remark. Geometric interpretation of system of linear equations. Remark. In a system of linear equations with two variables, x1, x2, each linear equation defines a line of x1, x2 plane. x1 times x2 plane. Okay, so since a solution to a system of linear equations must satisfy all equations simultaneously, the solution set is the intersection of these lines. This intersection set can be a line if the linear equations describe the same line. A point of or empty when the lines are parallel. An illustration is given in figure 2.3 for this system. This okay, so you have hold on, I just okay. 4x1 plus 4x2 is 5 and 2x1 minus 2x2 is equal to 1. Okay, for the solution space is the point x1, x2 and is 1, 4. So it has only for three variables. Each linear equation determines a plane, a three-dimensional space. When we intersect these planes and satisfy all linear equations at the same time, we can obtain a solution set that is a plane, a line, a point, or empty, when the planes have no common intersection. Okay, yeah, that makes sense. So in this case, it is a plane, right? Oh, wait. For a systematic approach to solving systems of linear equations, we will introduce a useful compact notation. We collect the coefficients aij into vectors and collect the vectors into matrices. In other words, we write the system from 2.3 in the following form. So this part multiplied by x1 and this multiplied by x2 and this multiplied by xn gives us b2 bn. That makes sense. Yeah, that makes sense. Right? Okay, we can multiply this by a vector. In the following example, we will have a close look how these matrices and define computation rules. We will return to solving linear equations in section 2.3. Okay. Matrices play a central role in linear algebra. They can be used to compactly represent systems of linear equations, but they also represent linear functions, linear mappings, yeah, as we will see later in section 2.7. Before we discuss some of these interesting topics, let us first define what a matrix is and what kind of operation we can do with matrices. We will see more properties of matrices in chapter 4. Definition 2.0 to 2.1. Matrix. With Mn as element of natural numbers, a real valued Mn matrix A is an n times n multiple of elements Aij, which I is equal is 1 to m and j is 1 to n, which is ordered according to a rectangular scheme consisting of m rows and n columns. Yeah, reading this in English is English is not my language, and reading this is a little bit weird. Like you're not used to. Like for me, these terms are new to me. So we have A equals to, okay, and this is pretty much how it works. So this is how we interpret linear equations using like the multiplication with a matrix and a with a matrix multiplied by a vector, and this gives us another vector which is b. That makes sense actually. So a matrix multiplied by a vector is a vector, right? Oh, so what the fuck is going on? Why is this? Why are my fans screaming? Oh, I don't know. by convention, 1 and n matrices 1n matrices are called rows, and m1 matrices are called columns. Wait. If we have m rows and n columns, but we have one row with column with multiple columns, wait, actually that makes sense. Yeah, that makes sense actually. Yeah. The M represents the rows, right? And rows and n columns. So we have, this is like, let's suppose we have this, and this is a m rows, like 3 times 1, like 3 by 1, and this can be 1, 2, 3, right? Or just you know wait, let me just do this right here, just like that. So let me try to create something. So we have a v. Okay, this is a vector. Then we have like x 1. Then we have x2 and x3, and v is part of this tuple, right? It's something like this, right? And then we have another vector. Let's call this u, and this is a this part here, and this is a column because this has m equals 3, but this one has n set to 3, right? This is basically how it works, and this makes sense. Okay, so A could be yes. Yeah, it's like it is like this, right? As A wait, this is a vector. By stacking all n columns of the matrix into a long vector. Oh, yeah, that's true. We can like do this. We can stack like this together, right? In this way. Yeah, yeah, we can do that, right? So we have the sum of two matrices A as element of the tuple or the matrix. Hello world. How are you? Welcome to the stream. are you? So this is actually how it works, right? So uh, what I'm doing right now is I'm trying to learn the basics of for linear algebra for machine learning. This could be useful for machine learning and my and university, right? Hold on, let me check if I still streaming because sometimes it suddenly interrupts and I honestly don't know why. Yeah, it's still streaming. Remember the Discord of the pink sheep? Oh wait. Oh wait, hold on, hold on. Wait. You mean this one? You mean this one, right? No way. Like you are one of the members here, right? Like what? Like are you serious? Wait, which one is you? Also, I apologize for my bad English, but it's not my native language. Wait, there is no way. Are you fun master or uh, this person or Johnny? Which one is you? Oh, that's cool. Like Jesus. Like I remember where I wanted to make a a server community or anything like that. It was wow. The, I'm surprised. Like I didn't expect that, honestly. Oh, let me say hi. Like do you wanna tell do you wanna tell me which one like like, which one is you? Because I'm just curious. Like, but wow, I didn't expect that, honestly. So yeah, this is okay. Let me introduce you to my channel. Like, this is where I usually stream. Like, I stream my own personal things to as I mentioned here. Like, I only stream to improve my communication skills, my English, and to keep track of what I'm doing. Like, and so I don't know why, but some people are actually interested of what I'm doing, and like some people subscribe to my channel, right? Eh, and they want to know me, and it's pretty cool. Actually, it's pretty cool. Also, I made this new intro right here. This one. Uh, I don't have headphones right now, but you can hold on. Let me just. I don't know if you can hear it, but I created this the last night. I used Adobe Premiere Pro. Let me just increase the quality. Uh, my internet sucks. Honestly, I didn't expect, like, and right now I'm wait, what is it? I'm trying to learn, this stuff to create language models, and it is useful because I'm studying software engineering, and yeah, that's basically. Thank you, thank you, hello world. Like, I'm. I don't know who are you exactly, but I'm so glad that we we met after, I don't know, 4 years. That's crazy. That's actually crazy. There is a lot of delay. Oh, I'm sorry. I My internet is not that great. Oh God, this isn't good. Okay. Yeah, that's crazy. I I totally didn't expect this. Like, wait, where the fuck is the? Oh, here it is. So right now I'm trying to, to learn OpenGL and this stuff right here, and it's pretty interesting. Like, this is the basically how machine learning works. Like, you have, um, yeah, it is. It is bad. It's literally, it's, trust me, it's really, really bad. And wait, how do you know I'm from Italy? Wait, how do you know? Just curious. So this is basically how machine learning works. You have data, and then there is the learning process where you get the patterns, using, like, you read this data, and the data is a vector, right? This is a vector, and the vector is, we can think of a set of elements, right? We have like element one, then we can represent it like this. It's we have element one, element two, and until we, you know, we can have, um, an undefined quantity of elements, right? Then we pass this to the learning models. Oh, I told you. Oh, sorry, I didn't remember that. Yeah, Italian connection is pretty bad, especially if you live in rural areas. Like, I don't live in a big city, or I live in a forest. Like, it isn't. This is. It's not probably the best. Then you have like the learning process, and you retrieve the patterns from the existing data. You try to, to retrieve the patterns, and the models. Uh, it was a long time ago. It's fine. Oh yeah. Yeah. You mean, like, I told you that a long time ago, right? And then, wait, we have the model, and then the model generates new data, and this is basically pretty much how prediction algorithms work. Like, we have, I don't know if you are like into financial stuff, but sometimes you have like brokers that have graphs, and these graphs make predictions about marketing stuff, and they probably use this type of algorithm. For now, I'm trying to learn the fundamentals, like the sorry, I struggle talking because uh, I'm not that used. And yeah, these are the fundamentals. We have linear algebra right here, and for now, I'm trying to, you know, to learn the operations I can do with matrices. And matrices are a really interesting part because I don't know if you're into computer science or anything like that. They are everywhere. Like matrices, you can create 3D worlds with matrices. Like I don't know if you noticed, but right here, hold on, let me uh, right here, like I also trying to learn OpenGL, which is a graphics library. It's a graphics API to, to create. Um, you can create a graphics application, including game engines, with that. And if you if you develop OpenGL, like if you program in OpenGL, you also need to understand like the basics of matrix transformation, because it's basically how 3D works. It's like um, it's like a free, it's like a vector. Like this is the origin, and you have a vector pointing a to a specific location, and then you have to calculate each movement you have, like each transformation. And this gives us the vectors. Like we can consider this arrow as vectors, like x, y, and then the third one, which is z, right? And if you sum these vectors, oh god, you get z, the other vector. It's really interesting how things work. And with more complex operations, you can render realistic graphics on your PC. Like, it's really interesting. Hold on, let me search OpenGL. You can see right here, like, it's a cross-platform. Like, you can create games with it. Like, you can create your own graphics. Like, it's not an engine. It's literally an interface to control your graphics card, your your GPU. This component here. This is how it's done. Like, there is some history, of course. Like, the one of the most powerful one is the NVIDIA RTX 5090. and this is one of the most expensive one you can find on the market on this spectrum. Jesus, it's almost $3,000. And yeah, the graphics card have open, like most of them have OpenGL. It's standard at this point. Oh, this is polynomial interpolation. Polynomial interpolation is is like a process to, you have a graph, then you have like some points right here. With the polynomial interpolation, you can find a function that um, that you know that calculates um, that you know you can find a function that how can I explain it in English, that encounters each point here. And there is another one called polynomial regression, which is a similar thing, but you can, it's very useful with statistics, which is uh, it's written right here. It's a form of regression analysis with which the relationship between the independent variable and the dependent variable y is modeled as polynomial. Okay, it's not that clear, but for what I can understand, it's this process where you can find a function that, like, where you get the pretty close to the points to make, a how can I say it in English? I don't know the English term for this, but the, you can pretty much understand. You get the function that almost encounters all of these points. So yeah. Oh wait, where is the? I'm surprised that some people are actually subscribed to my channel. Like, I only stream for my own thing. Like, I just code for myself, and people, some people are actually interested, and that makes me happy actually. Like, someone asked me how to do certain things with JavaScript, which is a language used in in browsers. Like, when you use a website, and you like and you can program the website, like, you when you click this button, it will play a certain animation. All of this is handled by JavaScript, which is run in your browser. Someone asked me, uh, like, some like asked me help and questions about that, and yeah, I'm really happy that there are people that, you know Yeah, exactly. Yeah. Yes, it's used when you do an experiment. Exactly. Yeah. Yeah, it's very used in Excel to get an estimated. Yeah, it's a useful calculation you do to make um, uh, what's the name like um, hold on I kind of forgot the exact term to describe what I wanted to describe, but yeah, it's really used for that. Then we have matrices. Yeah, I'm still on the basis. Like I decided to reread everything from scratch because I want to cover everything, so that could be useful. And after I learned everything about this part and OpenGL, I wanted to create a game. Like I wanted to make a game from scratch, like literally from scratch, without using Unity. I wanted to like it's an interesting one. Like I have mm, like it's a weird game where you there are many optical illusions and many tricky levels, and it's how can I describe it? Like it's weird. Like it's weird in a good way. Uh, Hold on, let me search for way weird car. It's something like this. Like the ambience is something like this. You know, I wanted to create something like this, and there are many optical illusions. Like there are many things, and it could be really interesting to try that out. Um, and maybe sell it on Steam. I like this image. Yeah, you have, it will be really tricky. Yeah, like minimal spaces. Yeah, exactly. Yeah, it's something like this with some object that are not supposed to be here. Like you will have, this plane here or this. I don't think I will put this flying floating milk right there, but you get the idea. Okay, let's see what we have to read about matrices. This means to compute the element Cij. We multiply the elements of the I totally skipped this part. The sum of two matrices A and B is defined as the element-wise sum. So A and B is actually, okay, this is like A1 1 plus B1 1. So if we have like two matrices, so let's say we have 1 2 3 4, and then we have plus 5 6 7 8. So this is A and this is B, right? We get the result. The result will be C, and this will be this is defined, okay, 1 and 1, so it would be, so it will be a matrix, right? And it should be 1 plus 5, then 2 plus 6, 3 plus 7, and 4 plus 8. This should be the solution, right? What do you mean we multiply? Wait, this means to compute element C, we multiply the elements of the ith row of A with the jth column of B and sum them up. Wait, where? Oh, is this a vector or a matrix? Like, this seems like it is a matrix, right? Because A and B is an element of the set R with m times k elements, right? And this means it is a matrix. Oh wait, this is another C. This is the lowercase c. I noticed that now. So we have this, which is a sum with L from 1. Okay. Yeah, this is a multiplication, right? Yeah, and then we sum them up. Oh, that's how we multiply it. Okay. Okay, basically, the book is now trying to explain how to multiply the matrices, not to sum up anymore. Only from the left side. So the product of B and A of the matrix B and A is not defined if M is not equal to N. So it must be like this. This is a little bit confusing. Then we have the properties of the matrices. Oh, these are all the properties. Okay. And then we can represent the linear equations like this. So these are the coefficients multiplied by each with the unknown variable, right? And this is the right side of the equation. So in this part, 2 is multiplied by the first element, and 3 is multiplied with the second element, and 5 is multiplied with the third element of the second of this vector. And then we repeat the process with all of the for all the rows, like for the my god, for each number, right? That's interesting. Also, this book also mentioned 3 blue, 1 brown, right? And I saw there is a 3 blue, 1 brown. There is this series. Let me try to find it. Wait, where is it? Oh, this one.
Did you know the average person spends 3.5 hours planning?
So this has many episodes about how matrix transformation work, and it provides with really good examples and animations, and I think it's pretty good. I want to try to watch the entire series, like to rewatch it, because I watched it before, but I kind of forgot everything. So, okay, let's see if I see streaming, because I don't know if I. Okay, I'm still streaming. That's cool. So, uh, for now, I will take a short break. I will eat something, and when I come back, we will try to watch this series, to watch this playlist, these videos, and try to, Oh, that's cool. That's cool. Yeah, there is a lot of delay because I mentioned it like 5 minutes ago, probably, and it's yeah. I wanted to watch all of this part right here because he's pretty good at explain this thing. Also, let me share my new Discord server. This is where like we talk about my projects and everything about like the things I do here. Let me share my new Discord server. Hold on. Let me try to. Wait. Where do I get the? Okay. So I have. Oh Jesus. How do I get the invite link? Wait, hold on. Let me just uh, let me just disable this. So we have no. So we have where is it? Um. Oh my God, this is frustrating. Here it is. Let me share this invite code. How can I copy the link? Wait, hold on. Oh, that's cool. That's cool. Um, in electric engineering and physics in general. Even though I'm not in uni yet, this is what I am for. That's cool. That's interesting. I'm on computer. I'm aiming for software engineering. I'm already in uni. This is my first year. You can already tell. Uh, yeah, I have some projects in mind, and this is a brand I created for for my software. Let me just hold on. Let me share my Discord invite. So I think the link should be like this, and then you paste it, right? Let me know if that works. It should. Yeah, I think it worked. Yeah, it should be working. So what I'm trying to do is I'm trying to, to create a community, and then share this stuff, and create like just people uh, trying to create something, like so if you want to join, there is this link right here, and I'm still trying to set it up. Like, there are the rules channel is completely empty, so everything is still in progress, but these are some project I have in mind. Also, let me just, oh, this is what I'm reading, by the way. It's called, you can search ML book. It's mathematics for machine learning, and it teaches you a lot of basics. And where is it? I cannot find it anymore. Yeah, this is pretty much. So let me check what the second part of the book, because this is where I this is the second part, and this should be it should be more practical. Yeah. Okay, right now I'm gonna take a short break. I'm gonna eat something. Uh, I will come back in a few minutes, and 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 what else I have to say? I forgot. I'm kinda nervous. I don't know why. So I'll see you later.
Okay, everyone, I'm back. Can you hear me? Okay, so I remember doing funny comments with Dunk Memer. Oh my god, yeah, I remember that bot. I remember. Also, we have new mentions here. Okay. Uh, because there was where is it? Right here. Uh, yeah, we had this. We had this bot right here, like, and we were like doing many things. I remember that. Like this is 4 years ago. Like, holy Jesus. And it's kind of weird that like that time has passed, and uh, let me check something real quick. So, okay, now let's try to deeply understand matrices, okay? Okay, we are way too far. Like, we um so uh we reached this point, right? Now let's try to understand how matrices work. Like, do we have oh my fucking god, do we have like uh, a free version of MATLAB free online? And this is not free, isn't it? No, it's not free. But we have this. Okay, that's interesting. Like, we can define vectors like a 1, 2, 3, 4. like that. Okay. And then we have ants, right? Wait. Oh, right. We need to, like, if we make this, the answer will be set to 2, right? Also, get the fuck out of here, you stupid ad. Wait, what the hell? Oh, there it is. Let me just. Oh my god, why is it lagging? So, where is this? This is the iframe, right? We will delete this because we don't need this. We don't need this stupid fucking useless element. Here we go. So this is how I learn, like I practice with scripting, because yeah, scripting is what I can do. The scripting is the best thing I can do. So let's use the scripting to learn how linear algebra works. So if we have like 1, 2, then we have, wait, I can just do this, right? Yep. If I remember correctly, MATLAB has this symbol to, to multiply um, and we get an error. So as you can see, it's 2 times 2. Wait, hold on. I'm dumb. I should do this. Yep. This is basically how it works. Like, you have the first element, you multiply with the first, and the second with the second element. Wait, and the second with the first, and then you sum it, right? So 2 times 3 is 6, plus 3 is, wait, no. 2 times 4 is 8, plus 3 is 11. Then we have 3 times 3 is 9, plus 16. And then we have 25. So this is basically how it works. So on the matrix, for what I understand, we have hold on. Let's suppose we have this, like we have A, B, C, D, and then we have E and F, right? We have something like this. Then we have to multiply A times, why did I write 2 instead of A? What the hell? A, E, plus BF, right? That's basically what we are doing. No. Then we have CE plus DF, and this should be basically how it works, right? What the heck? Get the fuck out of here. This shit is full of ads, but I don't care. Let's keep going. So what if we have a matrix? So let's do 1, 2, 3, then 4, 5, 6, then 7, 8, 9 with, I don't think we can multiply with this because it's not consistent, and I think it will throw an error. Yep, it throws an error. But what if we add a third element? Now it shouldn't be working. It should not be working, right? Let's try again. See it? Well, now let's turn it a vector of columns. And here we go. I mean a vector of rows. We get the multiplication. But can we do this? Like, can we do this thing? Let's see. Yep, we can. And the result is apparently the result is the lowest part, the lowest the matrix with the lowest count, with the lowest amount of rows and the amount of columns. Is it commutative? Let's check this out. What the hell? It is not. It is not commutative. So we don't have this commutative property. And that's interesting. So if we check this book, do we have the commutative property? We have associativity, we have distributivity, and we don't have anything else. Wait, what? That's it? Let's try to read more about this. This means the computing elements C, Y, J. We multiply the elements of the ith row A with the jth of column B and sum them up. Later, the section 3.2. We will call this the dot product. So this is the dot product. So what we did here is A times B, like the dot product, and A and B, oh shit, are actually A is, oh god, A is actually is an element of this set. It's a 4x4 matrix, and B is an element of the set of a tuple of 2 times 1 real numbers. And then we get a 2 plus 1, like this thing this thing gives us a new matrix, and it's 2 by 1. A new 2 by 1 matrix. This is basically how it works, right? Let's save this. I will call it SL, stands for Study and Learning 1. And let's create a new file. So matrices can only be multiplied if their neighboring dimensions match. For instance, an n by k matrix A can be multiplied with a k by m matrix B, but only from the left side. So that means this is, wait, I'm still confused on how this works. No, so now let's try to watch 3 Blue 1 Brown, because that's what we are going to do. Like, that's YouTube videos are the best. For me, are the best way to learn. So let's wait. Let me plug my headphones. Jesus Christ. Holy shit. And let's start watching it. So let me check if I'm still streaming, because oh wait. Yep, I am. And I'm streaming for 4 hours. Holy damn. This is oh my god. Wait, Herman? It's not new. This name is not new. Do you remember when we read that book and I clicked on a name and they fucking teleported me to the end of the book? Let's see if I... Oh, that's not Herman, that's Hoffman. Okay, the name is kinda similar, so... They are probably the same person. I'm kidding, if you didn't understand. So let's keep going.
The fundamental, root of it all building block for linear algebra is the vector. So it's worth
Yeah.
making sure that we're all on the same page about what exactly a vector is. You see, broadly speaking, there are 3 distinct but related ideas about vectors, which
The physics, the computer science definition, and the mathematical definition, right?
I'll call the physics student perspective, the computer science student perspective, and the mathematician's perspective. The physics student
Nice.
perspective is that vectors are arrows pointing in space. What defines a given vector is its length and the direction it's pointing. But as long as those two facts are the same, you can move it all around and it's still the same vector. Vectors that live in the flat plane are two-dimensional, and those sitting in broader space that you and I live in are three-dimensional. The computer science perspective is that vectors are ordered lists of numbers. For example, let's say you were doing some analytics about house prices, and the only features you cared about were square footage and price. You might model each house with a pair of numbers, the first indicating square footage and the second indicating price. Notice, the order matters here.
Yeah.
In the lingo, you'd be modeling houses as two-dimensional vectors, where in this context, vector is pretty much just a fancy word for list, and what makes it two-dimensional is the fact that the length of that list is 2. The mathematician, on the other hand, seeks to generalize both these views, basically saying that a vector can be anything where there's a sensible notion of adding two vectors and multiplying a vector by a number, operations that I'll talk about later on in this video. The details of this view are rather abstract, and I actually think it's healthy to ignore it until the last video of this series, favoring a more concrete setting in the interim. But the reason I bring it up here is that it hints at the fact that the ideas of vector addition and multiplication by numbers will play an important role throughout linear algebra. But before I talk about those operations, let's just settle in on a specific thought to have in mind when I say the word vector. Given the geometric focus that I'm shooting for here, whenever I introduce a new topic involving vectors, I want you to first think about an arrow, and specifically, think about that arrow inside a coordinate system, like the xy plane, with its tail sitting at the origin. This is a little bit different from the physics student perspective, where vectors can freely sit anywhere they want in space. In linear algebra, it's almost always the case that your vector will be rooted at the origin. Then, once you understand a new concept in the context of arrows in space, we'll translate it over to the list of numbers point of view, which we can do by considering the coordinates of the vector. Now, while I'm sure that many of you are already familiar with this coordinate system, it's worth walking through explicitly, since this is where all of the important back and forth happens between the two perspectives of linear algebra. Focusing our attention on two dimensions for the moment, you have a horizontal line, called the x-axis, and a vertical line, called the y-axis. The place where they intersect is called the origin, which you should think of as the center of space and the root of all vectors. After choosing an arbitrary length to represent 1, you make tick marks on each axis to represent this distance. When I want to convey the idea of 2D space as a whole, which you'll see comes up a lot in these videos, I'll extend these tick marks to make grid lines, but right now they'll actually get a little bit in the way. The coordinates of a vector is a pair of numbers that basically gives instructions for how to get from the tail of that vector at the origin to its tip. The first number tells you how far to walk along the x-axis, positive numbers indicating rightward motion, negative numbers indicating leftward motion, and the second number tells you how far to walk parallel to the y-axis after that, positive numbers indicating upward motion, and negative numbers indicating downward motion. To distinguish vectors from points, the convention is to write this pair of numbers vertically, with square brackets around them. Every pair of numbers gives you one and only one vector, and every vector is associated with one and only one pair of numbers. What about in 3 dimensions? Well, you add a third axis, called the z-axis, which is perpendicular to both the x and y axes, and in this case, each vector is associated with an ordered triplet of numbers. The first tells you how far to move along the x-axis, the second tells you how far to move parallel to the y-axis, and the third one tells you how far to then move parallel to this new z-axis. Every triplet of numbers gives you one unique vector in space, and every vector in space gives you exactly one triplet of numbers. Alright, so back to vector addition and multiplication by numbers. After all, every topic in linear algebra is going to center around these two operations. Luckily, each one's pretty straightforward to define. Let's say we have two vectors, one pointing up and a little to the right, and the other one pointing right and down a bit. To add these two vectors, move the second one so that its tail sits at the tip of the first one. Then, if you draw a new vector from the tail of
that's
the
the
first
sum,
one
right?
to where the tip of the second one now sits, that new vector is their sum.
Yep.
This definition of addition, by the way, is pretty much the only time in linear algebra where we let vectors stray away from the origin. Now, why is this a reasonable thing to do? Why this definition of addition and not some other one? Well, the way I like to think about it is that each vector represents a certain movement, a step with a certain distance and direction in space. if you take a step along the first vector, then take a step in the direction and distance described by the second vector, the overall effect is just the same as if you moved along the sum of those two vectors to start with. You could think about this as an extension of how we think about adding numbers on a number line. One way that we teach kids to think about this, say with 2 plus 5, is to think of moving 2 steps to the right, followed by another 5 steps to the right. The overall effect is the same as if you just took 7 steps to the right. In fact, let's see how vector addition looks numerically. The first vector here has coordinates 1, 2. And the second one has coordinates 3, negative 1. When you take the vector sum using this tip-to-tail method, you can think of a 4-step path from the origin to the tip of the second vector. Walk 1 to the right, then 2 up, then 3 to the right, then 1 down. Reorganizing these steps so that you first do all of the rightward motion, then do all the vertical motion, you can read it as saying, first move 1 plus 3 to the right, then move 2 minus 1 up. So the new vector has coordinates 1 plus 3 and 2 plus negative 1. In general, vector addition in this list of numbers conception looks like matching up their terms and adding each one together. The other fundamental vector operation.
What? There's a typo? Oh, he has. This person has a website? Whoa. They also have Blue Sky. Okay. Where is it?
Is multiplication by a number. Now this is best understood just by looking at a few examples. If you take the number 2 and multiply it by a given vector, it means you stretch out that vector so that it's 2 times as long as when you started. If you multiply that vector by, say, 1/3, it means you squish it down so that it's 1/3 the original length. When you multiply it by a negative number, like negative 1.8, then the vector first gets flipped around, then stretched out by that factor of 1.8. This process of stretching or squishing or sometimes reversing the direction of a vector is called scaling. And whenever you catch a number, like 2 or 1/3 or negative 1.8, acting like this, scaling some vector, you call it a scalar. In fact, throughout linear algebra, one of the main things that numbers do is scale vectors, so it's common to use the word scalar pretty much interchangeably with the word number. Numerically, stretching out a vector by a factor of, say, 2, corresponds with multiplying each of its components by that factor, 2. So in the conception of vectors as lists of numbers, multiplying a given vector by a scalar means multiplying each one of those components by that scalar. You'll see in the following videos what I mean when I say that linear algebra topics tend to revolve around these two fundamental operations, vector addition and scalar multiplication. And I'll talk more in the last video about how and why the mathematician thinks only about these operations, independent and abstracted away from however you choose to represent vectors. In truth, it doesn't matter whether you think about vectors as fundamentally being arrows in space, like I'm suggesting you do, that happen to have a nice numerical representation, or fundamentally as lists of numbers that happen to have a nice geometric interpretation. The usefulness of linear algebra has less to do with either one of these views than it does with the ability to translate back and forth between them. It gives the data analyst a nice way to conceptualize many lists of numbers in a visual way, which can seriously clarify patterns in data and give a global view of what certain operations do. And on the flip side, it gives people like physicists and computer graphics programmers a language to describe space and the manipulation of space using numbers that can be crunched and run through a computer. When I do mathy animations, for example, I start by thinking about what's actually going on in space and then get the computer to represent things numerically, thereby figuring out where to place the pixels on the screen. And doing that usually relies on a lot of linear algebra understanding. So there are your vector basics, and in the next video, I'll start getting into some pretty neat concepts surrounding vectors, like span, bases, and linear dependence. See you then.
That's interesting. Let's move on. Oh my fucking god. Oh my god, don't do this.
In the last video, along with the ideas of vector addition and scalar multiplication, I described vector coordinates, where there's this back and forth between, for example, pairs of numbers and two-dimensional vectors. Now, I imagine the vector coordinates were already familiar to a lot of you, but there's another kind of interesting way to think about these coordinates, which is pretty central to linear algebra. When you have a pair of numbers that's meant to describe a vector, like 3, -2, I want you to think about each coordinate as a scalar, meaning think about how each one stretches or squishes vectors. In the xy coordinate system, there are two very special vectors. The one pointing to the right with length 1, commonly called I hat, or the unit vector in the x direction, and the one pointing straight up with length 1, commonly called j hat, or the unit vector in the y direction. Now, think of the x-coordinate of our vector as a scalar that scales I hat, stretching it by a factor of 3. And the
Wait. What's the name of this two? There was a name, right?
Coordinate system, there are two very special vectors. The one pointing to the right with length 1, commonly called I hat, or the unit vector in the x direction, and the one pointing straight up with length 1, commonly called j hat, or the unit vector in the y direction. Now, think of the x-coordinate
They had a specific term. I don't remember the name.
of our vector as a scalar that scales I hat, stretching it by a factor of 3, and the y-coordinate as a scalar that scales j hat, flipping it and stretching it by a factor of 2. In this sense, the vector that these coordinates describe is the sum of two scaled vectors. That's a surprisingly important concept, this idea of adding together two scaled vectors. Those two vectors, I hat and j hat, have a special name, by the way.
Oh,
Together, they're called the basis of a coordinate system.
yeah.
What this means, basically, is that when you think about coordinates as scalars, the basis vectors are what those scalars actually, scale. There's also a more technical definition, but I'll get to that later. By framing our coordinate system in terms of these two special basis vectors, it raises a pretty interesting and subtle point. We could have chosen different basis vectors and gotten a completely reasonable new coordinate system. For example, take some vector pointing up and to the right, along with some other vector pointing down and to the right in some way. Take a moment to think about all the different vectors that you can get by choosing two scalars, using each one to scale one of the vectors, then adding together what you get. Which two-dimensional vectors can you reach by altering the choices of scalars?
Oh wait, that's right. The basis of the vector. If you alter the basis, the basis vectors, you have completely different results, right? It's like when you are in a 2D plane and there is a camera. The camera moves, and everything gets more. Everything gets shifted for somehow, and on the physical position in the screen, it's not the same. Like, I don't know how can I explain this, but yeah, it's something like this, right? You if you alter the basis, like you create like a new a new system, like, and you have completely different results, right?
The answer is that you can reach every possible two-dimensional vector, and I think it's a good puzzle to contemplate why. A new pair of basis vectors like this still gives us a valid way to go back and forth between pairs of numbers and two-dimensional vectors, but the association is definitely different from the one that you get using the more standard basis of I hat and j hat. This is something I'll go into much more detail on later, describing the exact relationship between different coordinate systems. But for right now, I just want you to appreciate the fact that anytime we describe vectors numerically, it depends on an implicit choice of what basis vectors we're using. So anytime that you're scaling two vectors and adding them like this, it's called a linear combination of those two vectors.
So we
Where does
have uh, so we have a linear combination if we like if we perform any every operation or just the sum.
this word linear come from? Why does this have anything to do with lines?
Wait.
Choice of what basis vectors we're using. So anytime that you're scaling two vectors and adding them like this, it's called a linear combination of those two vectors
Hold on.
between different coordinate systems. But for right now, I just want you to appreciate the fact that anytime we describe vectors numerically, it depends on an implicit choice of what basis vectors we're using. So anytime that you're scaling two vectors and adding them like this, it's called a linear combination of those two vectors.
Okay, both operations. Okay.
Where does this word linear come from? Why does this have anything to do with lines? Well, this isn't the etymology, but one way I like to think about it is that if you fix one of those scalars and let the other one change its value freely, the tip of the resulting vector draws a straight line. Now, if you let both scalars range freely and consider every possible vector that you can get, there are two things that can happen. For most pairs of vectors, you'll be able to reach every possible point in the plane. Every two-dimensional vector is within your grasp. However, in the unlucky case where your two original vectors happen to line up, the tip of the resulting vector is limited to just this single line passing through the origin. Actually, technically there's a third possibility too. Both your vectors could be zero, in which case you'd just be stuck at the origin. Here's some more terminology. The set of all possible vectors that you can reach with a linear combination of a given pair of vectors is called the span of those two vectors.
Oh, what the? No.
Dimensional vectors.
Oh
But
god.
the association is definitely different from the
I
you
was.
can reach
Yeah.
with a linear.
I want to pause the video, but I'm fucking stupid and I skipped over. So the span of V and WV is the set of all their linear combinations. So, okay, so
combination of a given pair of vectors is called the span of those two vectors. So restating what we just saw in this lingo, the span of most pairs of 2D vectors is all vectors of 2D space. But when they line up, their span is all vectors whose tip sit on a certain line. Remember how I said that linear algebra revolves around vector addition and with lines?
wait.
Well, this isn't the etymology, but one way I like to think about it is that if you fix one of those scalars and let the other one change its value freely, the tip of the resulting vector draws a straight line. Now, if you let both scalars range freely and consider every possible vector that you can get, there are two things that can happen. For most pairs of vectors, you'll be able to reach every possible point in the plane. Every two-dimensional vector is within your grasp. However, in the unlucky case where your two original vectors happen to line up, the tip of the resulting vector is limited to just this single line passing through the origin. Actually, technically there's a third possibility too. Both your vectors could be zero, in which case you'd just be stuck at the origin. Here's some more terminology. The set of all possible vectors that you can reach with a linear combination of a given pair of vectors is called the span of those two vectors.
Oh, okay.
So restating what we just saw in this lingo, the span of most pairs of 2D vectors is all vectors of 2D space. But when they line
Yeah.
up, their span is all vectors whose tip sit on a certain line. Remember how I said that linear algebra revolves around vector addition and scalar multiplication? Well, the span of two vectors is basically a way of asking what are all the possible vectors you can reach using only these two fundamental operations, vector addition and scalar multiplication. This is a good time to talk about how people commonly think about vectors as points. It gets really crowded to think about a whole collection of vectors sitting on a line, and more crowded still to think about all two-dimensional vectors all at once, filling up the plane. So when dealing with collections of vectors like this, it's common to represent each one with just a point in space. The point at the tip of that vector where, as usual, I want you thinking about that vector with its tail on the origin. That way, if you want to think about every possible vector whose tip sits on a certain line, just think about the line itself. Likewise, to think about all possible two-dimensional vectors all at once, conceptualize each one as the point where its tip sits. So, in effect, what you'll be thinking about is the infinite flat sheet of two-dimensional space itself, leaving the arrows out of it. In general, if you're thinking about a vector on its own, think of it as an arrow. And if you're dealing with a collection of vectors, it's convenient to think of them all as points. So for our span example, the span of most pairs of vectors ends up being the entire infinite sheet of two-dimensional space. But if they line up, their span is just a line.
Yep.
The idea of span gets a lot more interesting if we start thinking about vectors in three-dimensional space. For example, if you take two vectors in 3D space that are not pointing in the same direction, what does it mean to take their span? Well, their span is the collection of all possible linear combinations of those two vectors, meaning all possible vectors
It's a
you
plane.
get by scaling each of the two of them in some way and then adding them together. You can kind of imagine turning two different knobs to change the two scalars defining the
It's
linear
a 2D
combination,
plane
adding the
inside.
scaled vectors and following the tip of the resulting vector. That tip will trace out some kind of flat sheet cutting through the origin of three-dimensional space. This flat sheet is the span of the two vectors.
Yeah.
Or more precisely, the set of all possible vectors whose tips sit on that flat sheet is the span of your two vectors. Isn't that a beautiful mental image? So what happens if we add a third vector and consider the span of all three of those guys?
Well, if they aren't lined up, it should take the whole 3D space, right?
A linear combination of three vectors is defined pretty much the same way as it is for two. You'll choose three different scalars, scale each of those vectors, and then add them all together. And again, the span of these vectors is the set of all possible linear combinations.
In this case, it should be the whole
Two different
3D.
things could happen here. If your third vector happens to be sitting on the span of the first two, then the span doesn't change. You're sort of trapped on that same flat sheet. In other words, adding a scaled version of that third vector to the linear combination doesn't really give you access to any new vectors. But if you just randomly choose a third vector, it's almost certainly not sitting on the span of those first two. Then, since it's pointing in a separate direction, it unlocks access to every possible three-dimensional vector. One way I like to think about this is that as you scale that new third vector, it moves around that span sheet of the first two, sweeping it through all of space. Another way to think about it is that you're making full use of the three freely changing scalars that you have at your disposal to access the full 3 dimensions of space. Now, in the case where the third vector was already sitting on the span of the first two, or the case where two vectors happen to line up, we want some terminology to describe the fact that at least one of these vectors is redundant, not adding anything to our span. Whenever this happens, where you have multiple vectors and you could remove one without reducing the span, the relevant terminology is to say that they are linearly dependent. Another way of phrasing that.
Oh, okay, that's interesting. So, okay, so these two are linearly dependent, right? Yeah, it's written right here.
Would be to say that one of the vectors can be expressed as a linear combination of the others, since it's already in the span of the others. On the other hand, if each vector really does add another dimension to the span, they're said to be linearly independent. So with all of that terminology, and hopefully with some good mental images to go with it, let me leave you with a puzzle before.
So they are linearly independent if the sum of this vector does not equal to this one. Okay, yeah, that's the third vector, right? So the sum of this for all values on A and B, this vector does not exist. Like it's not equal because it's outside of the current plane. Like they are, but they are, here.
So with all of that terminology, and hopefully with some good mental images to go with it, let me leave you with a puzzle before we go. The technical definition of a basis of a space is a set of linearly independent vectors that span that space. Now, given how I described a basis earlier, and given your current understanding of the words span and linearly independent, think about why this definition would make sense.
Yeah, of course it makes sense, because if you have a coordinate system, like the basis, like we can think that the bases are constructing the coordinate system, and if they are linearly dependent, they don't have they don't construct any, like, how can I explain this shit? So this is y, and this is y, and this is j, right? So this, in this case, this to construct a linear a linear dependent, like these two are linear independent because they make a coordinate system. These two are not. This doesn't create anything. Like, these two can be seen as one vector, right? And this doesn't generate any other vector outside this line. So this doesn't create, like, these two don't create a coordinate system, but it actually does. But you know what I mean. Okay.
In the next video, I'll get into matrices and transforming space. See you then.
Oh, this is where he introduces the images.
Vision spaccai.
Oh my fucking god. What the fuck, bro? Don't fucking do this shit. Why am I... Hold on. Why is OBS taking so much memory? Holy shit. Am I still streaming, by the way? Yes, I am.
Hey everyone. If I had to choose just one topic that makes all of the others in linear algebra start to click, and which too often goes unlearned the first time a student takes linear algebra, it would be this one. The idea of a linear transformation and its relation to matrices. For this video, I'm just going to focus on what these transformations look like in the case of 2 dimensions, and how they relate to the idea of matrix vector multiplication. In particular...
Let me release... I'm gonna replay this part.
Hey everyone. If I had to choose just one topic that makes all of the others in linear algebra start to click, and which too often goes unlearned the first time a student takes linear algebra, it would be this one. The idea of a linear transformation and its relation to matrices. For this video, I'm just going to focus on what these transformations look like in the case of 2 dimensions, and how they relate to the idea of matrix vector multiplication. In particular, I want to show you a way to think about matrix vector multiplication that doesn't rely on memorization. To start, let's just parse this term, linear transformation. Transformation is essentially a fancy word for function. It's something that takes in inputs and spits out an output for each one. Specifically, in the context of linear algebra, we like to think about transformations that take in some vector and spit out another vector. So why use the word transformation instead of function if they mean the same thing? Well, it's to be suggestive of a certain way to visualize this input-output relation. You see, a great way to understand functions of vectors is to use movement. If a transformation takes some input vector to some output vector, we imagine that input vector moving over to the output vector. Then to understand the transformation as a whole, we might imagine watching every possible input vector move over to its corresponding output vector. It gets really crowded to think about all of the vectors all at once, each one as an arrow. So, as I mentioned last video, a nice trick is to conceptualize each vector not as an arrow, but as a single point, the point where its tip sits. That way, to think about a transformation taking every possible input vector to some output vector, we watch every point in space moving to some other point. In the case of transformations in 2 dimensions, to get a better feel for the whole shape of the transformation, I like to do this with all of the points on an infinite grid. I also sometimes like to keep a copy of the grid in the background, just to help keep track of where everything ends up relative to where it starts. The effect for various transformations moving around all of the points in space is, you've got to admit, beautiful. It gives the feeling of squishing and morphing space itself. As you can imagine, though, arbitrary transformations can look pretty complicated. But luckily, linear algebra limits itself to a special type of transformation, ones that are easier to understand, called linear transformations. Visually speaking, a transformation is linear if it has 2 properties. All lines must remain lines without getting curved, and the origin must remain fixed in place. For example, this right here would not be a linear transformation, since the lines get all curvy. And this one right here, although it keeps the line straight, is not a linear transformation, because it moves the origin. This one here fixes the origin, and it might look like it keeps lines straight, but that's just because I'm only showing the horizontal and vertical grid lines. When you see what it does to a diagonal line, it becomes clear that it's not at all linear, since it turns that line all curvy. In general, you should think of linear transformations as keeping grid lines parallel and evenly spaced. Some linear transformations are simple to think about, like rotations about the origin. Others are a little trickier to describe with words. So how do you think you could describe these transformations numerically? If you were, say, programming some animations to make a video teaching the topic, what formula do you give the computer so that if you give it the coordinates of a vector, it can give you the coordinates of where that vector lands? It turns out that you only need to record where the 2 basis vectors, I hat and j hat, each land, and everything else will follow from that. For example, consider the vector v with coordinates -1, 2, meaning that it equals -1 times I hat plus 2 times j hat. If we play some transformation and follow where all go, the property that grid lines remain parallel and evenly spaced has a really important consequence. The place where v lands will be -1 times the vector where I hat landed plus I hat. It turns out that you only need to record where the 2 basis vectors, I hat and j hat, each land, and everything else will follow from that. For example,
that's cool.
Consider the vector v with coordinates -1, 2, meaning that it equals -1 times I hat plus 2 times j hat. If we play some transformation and follow where all 3 of these vectors go, the property that grid lines remain parallel and evenly spaced has a really important consequence. The place where v lands will be -1 times the vector where I hat landed plus 2 times the vector where j hat landed. In other words, it started off as a certain linear combination of I hat and j hat, and it ends up as that same linear combination of where those 2 vectors landed. This means you can deduce where v must go based only on where I hat and j hat each land. This is why I like keeping a copy of the original grid in the background. For the transformation shown here, we can read off that I hat lands on the coordinates 1, -2. and j hat lands on the x-axis over at the coordinates 3, 0. This means that the vector represented by -1 I hat plus 2 times j hat ends up at -1 times the vector 1, -2 plus 2 times the vector 3, 0. Adding that all together, you can deduce that it has to land on the vector 5, 2. This is a good point to pause and ponder, because it's pretty important.
Wait, hold on. So we have 5 and 2, right? Oh, that makes sense.
Now, given that I'm actually showing you the full transformation, you could have just looked to see that V has the coordinates 5, 2. But the cool part here is that this gives us a technique to deduce where any vectors land so long as we have a record of where I hat and j hat each land, without needing to watch the transformation itself. Write the vector with more general coordinates, x and y, and it will land on x times the vector where I hat lands, 1, -2, plus y times the vector where j hat lands, 3, 0. Carrying out that sum, you see that it lands at 1x plus 3y, -2x plus 0y. I give you any vector, and you can tell me where that vector lands using this formula. What all of this is saying is that a two-dimensional linear transformation is completely described by just 4 numbers, the 2 coordinates for where I hat lands and the 2 coordinates for where j hat lands. Isn't that cool? It's common to package these coordinates into a 2x2 grid of numbers, called a 2x2 matrix, where you can interpret the columns as the 2 special vectors where I hat and j hat each land. If you're given a 2x2 matrix describing a linear transformation and some specific vector, and you want to know where that linear transformation takes that vector, you can take the coordinates of the vector, multiply them by the corresponding columns of the matrix, then add together what you get. This corresponds with the idea of adding the scaled versions of our new basis vectors. Let's see what this looks like in the most general case, where your matrix has entries A, B, C, D. And remember, this matrix is just a way of packaging the information needed to describe a linear transformation. Always remember to interpret that first column, AC, as the place where the first basis vector lands, and that second column, BD, as the place where the second basis vector lands. When we apply this transformation to some vector xy, what do you get? Well, it'll be x times AC plus y times BD. Putting this together, you get a vector ax plus by, cx plus dy. You could even define this as matrix vector multiplication when you put the matrix on the left of the vector like it's a function. Then, you could make high schoolers memorize this without showing them the crucial part that makes it feel intuitive. But isn't it more fun to think about these columns as the transformed versions of your basis vectors, and to think about the result as the appropriate linear combination of those vectors? Let's practice describing a few linear transformations with matrices. For example, if we rotate all of space 90 degrees counterclockwise, then I hat lands on the coordinates 0, 1. And j hat lands on the coordinates -1, 0. So the matrix we end up with has columns 0, 1, -1, 0.
Oh, that's the fucking rotation. That's the fucking rotation matrix.
To figure out what happens to any vector after a 90-degree rotation, you could just multiply its coordinates by this matrix. Here's a fun transformation with a special name, called a shear. In it, I hat remains fixed, so the first column of the matrix is 1, 0. But j hat moves over to the coordinates 1, 1, which become the second column of the matrix. And at the risk of being redundant here, figuring out how a shear transforms a given vector comes down to multiplying this matrix by that vector. Let's say we want to go the other way around, starting with a matrix, say with columns 1, 2, and 3, 1, and we want to deduce what its transformation looks like. Pause and take a moment to see if you can imagine it. Starting with a matrix, say with columns 1, 2, and 3, 1, and we want to deduce what its transformation looks like.
So 1, 2, and 3, 1. So 1, 2, and then 3 1. Wait, does this reflect? Does this graph reflect? So 2 1 and wait, 2 1, and then we have what 1 2, and then we have 3 1. So the x and y coordinates kind of switch, right?
Pause and take a moment to see if you can imagine it. One way to do this is to first move I hat to 1 2, then move j hat to 3 1, always moving the rest of space in such a way that keeps grid lines parallel and evenly spaced.
Yeah, they kind of switch,
If the vectors
right?
that I hat and j hat land on are linearly dependent, which, if you recall from last video, means that one is a scaled version of the other, it means that the linear transformation squishes all of 2D space onto the line where those two vectors sit, also known as the one-dimensional span of those two linearly dependent vectors. To sum up, linear transformations are a way to move around space such that grid lines remain parallel and evenly spaced, and such that the origin remains fixed. Delightfully, these transformations can be described using only a handful of numbers, the coordinates of where each basis vector lands. Matrices give us a language to describe these transformations, where the columns represent those coordinates, and matrix vector multiplication is just a way to compute what that transformation does to a given vector. The important takeaway here is that every time you see a matrix, you can interpret it as a certain transformation of space. Once you really digest this idea, you're in a great position to understand linear algebra deeply. Almost all of the topics coming up, from matrix multiplication to determinants, change of basis, eigenvalues, all of these will become easier to understand once you start thinking about matrices as transformations of space. Most immediately, in the next video, I'll be talking about multiplying two matrices together. See you then.
Well, so basically, we can think of the basis vector when we transform other vectors, right? Like we just multiply for the new position of the new vector, right? Now let's try that out. So if we have this, okay, and then we have this vector right here, and this sits on this point. Just do this, and then okay, for me it's like, and then we change the coordinate system. Like we want to, to multiply this vector right here. So it's just a 3 by 3. I don't care. And then we want to multiply it by 5 and 7, right? We can multiply this. 5 is this, so it should be something like this, right? probably. And then we have to transform the new position or anything like that. Let me take a short break.